Hi, welcome to our next demonstration of the DSTS detection system. For the next demonstration, we're going to try to measure changes in temperature along a section of fiber within a 50 kilometer fiber assembly. So total round trip is 50 kilometers, which would be useful for, say, measuring a 25 kilometer long pipeline, where the fiber has to go out 25 kilometers and then come back 25 kilometers. We're going to show a couple of different variations, beginning with showing you how you make a standard measurement for detecting changes in temperature over a 2.5 meter long section of the fiber. After that, we'll follow up with a fast measurement technique, which is good for just detecting a change, say for fire detection, where you're not concerned so much about how accurate the measurement is, but quickly detecting a change in temperature. Let's go over our setup. We have our DSTS unit here. One fiber is connected to a 25 kilometer long reel. From there we have a 3 meter length of fiber where 2.5 meters are coiled into a small coil, and that leads to a second 25 kilometer reel which goes back to the Brillouin sensor. So, as in all sorts of measurements of this nature, we'll first take a baseline measurement and then an actual measurement showing changes in temperature caused from exposure, in this case from the simple heat of my hand. Let's get started. Alright, so as usual, we start by taking a baseline measurement. So, we start our recording. Now this will take a while. We're working with 50 kilometers of fiber, and we want to demonstrate the ability to detect changes in temperature over only a 2.5 meter section of fiber. So we have the instrument set up with a 25 nanosecond pulse width, where the pulse is actually going down through the fiber. The spatial steps that we've chosen is 1 meter. Okay? So it's less than half of the section covered by the pulse width. We have our averaging set for 4,000 averages. We're using a 300 megahertz scanning range, and we're taking measurements every 5 megahertz. Okay? All of these factors affect both the accuracy and the time taken to make a measurement. The shorter the pulse, the shorter the distance over which you will detect changes in temperature. However, you are limited by the total length of the fiber to a certain minimum pulse width. The shorter you make the spatial steps, the more data the instrument has to gather. The more averages you take, the more accurate the measurement will be taken compared to the noise signal. But again, more time taken to take these measurements. The larger the frequency range you cover, the larger the range in temperatures you can measure. But again, you're taking more measurements to cover that entire frequency range. Similarly, the more steps you take, or the smaller steps you take in terms of frequency, the more accurate you get your Brillouin sensor curve, but again, more time. So part of the process in setting up an instrument is to determine how much time you're willing to spend to take accurate readings versus quick readings. That's a trade-off you have to make as a user of the instrument. Right now we've almost finished collecting all of the data from our baseline reading. We are 96% of the way there. 99%. It's gathered the data, and now it's making an analysis of the spectrum. Again, more data means more time taken to analyze it as well. We're using the fast general process here for making these measurements for our demonstration. Later on, we'll be showing you the fast detection method, which will show you a much quicker way to take a reading, though with less accuracy. 50% of the way there. So this will take about a minute to a minute and a half to complete all of the analysis that we're doing here. Once I have the spectrum baseline recorded, we'll show a couple of points on the screen so you can see the spectrum, and also show you the 6-meter long section that is of, the 2.5-meter long section, which is of interest to us right now. 95%, 99%, and we have data. So now that we've gotten our initial baseline reading, we're now set to take a measurement. So I'll just put my hand over this section of fiber. Click on measurement. Make sure that it's on strain and temperature. Be sure that my signal's on temperature. And I start the recording method. So now, we are now taking the spectral off the fiber, and we will see a change in the spectrum, reflecting a change in temperature caused by my hand on this section of fiber. Room temperature here is about 25 degrees. Body temperature is about 37 degrees, but the temperature in hand is typically lower. It's typically around about 3 or 4 degrees lower than your body temperature. So you should see something around about 33 degrees for your hand temperature. Okay? So that would correspond to a temperature shift of about 8 degrees. Okay? Now, the fiber is going to see basically an average between my hand temperature and the temperature below the paper, so we may see something smaller as a result of this test. Also, I want to point out that this is a 2.5-meter section of fiber, and we're working with 25 nanosecond pulses, which is equivalent to a 2.5-meter section of the fiber. Okay? So we're really up to the resolution limit of the instrument here in terms of detecting this change in the temperature. If we really want to make sure that the precise measurement is being made, we should be looking over sections of the fiber roughly twice the resolution of the instrument. Okay? This is in accordance with standard sampling theory, which says in order to get accurate data of changes, you should be looking over sections roughly twice the resolution of your instrument. We're about 84% of the way through. Okay. Again, it's a two-stage process. We gather the data, and then we analyze the data. So once it's finished gathering the data, I can take my hand off the fiber. 97% of the way there. 99%. And now it's gathering the data. Now it's analyzing the data. So I can safely take my hand off now because it's finished taking the data for making this temperature measurement. All right. So it's always a two-stage process. Gather the data, then analyze the data. So, as I said earlier, this is the fast general analysis process that we're using here for this measurement. Okay? If I wanted to be super precise, I would be using the general analysis function in the instrument. But this is good enough for the purpose of this demonstration. 76% of the way there. 87% of the way there. And we have data. So now that we have the data, we can analyze it. So if you look carefully in the center of the screen, there's a small blip. And if we engage the zoom, we can zoom in on this region. There's our spike right there. And if we look here at 25 kilometers and 38 meters, we're at our baseline temperature, basically a variation of only about 0.3 degrees. 3 meters up, this is where my hand was, and we see a 5-degree increase in the temperature. As I mentioned earlier, room temperature here is about 25 degrees. My hand temperature is a few degrees below my core body temperature, so it's about 33 degrees. That's a temperature difference of 8 degrees, and the fiber is seeing the average between my hand on the top and the table beneath. So a 5-degree reading in the temperature is quite reasonable. Bear in mind as well that with the pulse width of 25 nanoseconds, our resolution of the instrument is only 2.5 meters, okay? So we are seeing discrete changes here going only about 2-3 meters in. We can see that change. And again, going from the 25 kilometers and 42 meters down to 25 kilometers and 45 meters, again about 3 meters, we're back to our zero reading. So this shows that we can detect the changes in temperature with 2.5 meter resolution, okay, over a 50 kilometer length of fiber. So let's now demonstrate our fast measurement system. This is actually a very useful tool for things like fire detection or detection of some sort of catastrophic or disaster failure where you want to be able to see something happening in a fast turnaround frame. Okay? Again, we have to start off making a baseline measurement. Now the baseline measurement takes time. However, once we have our baseline measurement made, measurements made after that are done quickly, hence the fast measurement process. So let's start off by taking the initial baseline reading. So it's now started off taking a baseline reading. We made a couple of small changes to the parameters here. We've gone from a 25 nanosecond peak nanosecond pulse width to a 50 nanosecond pulse width. That's decreasing our resolution to only 5 meters. So now when I try measuring the signal in my hand, it's going to average my hand temperature with the temperature in the neighboring section of fiber. So we won't see as large as change as temperature, but we will see a change in temperature. We've also lowered our spatial steps to 2 meters instead of 1 meter. But all the other parameters in terms of the averaging, in terms of the frequency range, we've kept the same. 90% of the way through, so once we have this data, we'll show the measurement being made. 95% of the way, 99%, and now it does the data analysis. Fortunately, the analysis of the data is a bit faster than the gathering of the data, so we don't have to wait quite so long. We're already about 40% of the way through analyzing the data. Again, taking accurate measurements initially allows us to make the rapid measurements afterwards. 80%, 90%, done. So that's our baseline measurement. Now that we have our baseline reading, let's demonstrate the actual fast measurement system. So I'm going to choose disaster warning. Click on fast measurement. I'll put my hand onto the fiber And I'll start. Select temperature and start the measurement. So before it took us several minutes to actually take a full reading. Right now, in a period of just a matter of a few seconds, we've already gathered the data, and now it's doing the analysis. And it's completed. So that is a much faster process. And if we zoom in to this area in question, again, we can see a spike. The peak is about 5 degrees again above the background. And now it's about 4 or 5 meters below on one side for the peak. And again on the other side it's about 5 meters because we lowered our resolution by going to a 50 nanosecond pulse instead of a 25 nanosecond pulse. Okay? But again, we are able to see that change in temperature over a range going from 37 meters, 25 kilometers and 37 meters, 25 kilometers and 41 meters, 25 kilometers and 51 meters. So over a range of effectively 15 meters, we see our spike in the change in the temperature.